Today is Wednesday, March 26th, 2025. This is Bryan Gable and Joey Reynolds with the National Corvette Museum. Today we are in Madison Heights, Michigan at Werner Meyer's Automobile Restoration Shop, and we're talking with George Heberling and Tom Langdon, and we are going to focus this interview on the history of the ZL1 Corvette. So I'll ask you guys if you could give me a brief introduction about yourselves, your background, your connections with the Corvette and General Motors. George, if you'd like to start, please.
Well, I started with General Motors in 1954, so I've been around a while. I managed to work for them for 41 years and had a variety of products, but I was resident engineer on the Corvette in 1969 down in the St. Louis assembly plant. And that's when we got to initiate the ZL1 engine into the Corvette, which was a major project because not just the engine, because that's very similar or identical to the regular big block, but one of the most interesting things on that is being able to put the stripe on the front of the car, because that was a masking job that had to be done, and we only really built one of them, as far as I am aware of, and the plant was always concerned that in doing the paint job, if they screwed up the mask on the thing, that they would have to wait a while to get a new masking job, so they were concerned about building that car, and so it was a big event in the assembly plant from that standpoint, and I was part of that process, and I was fortunate enough to drive the car as a company car.
And Tom, if you could provide us with a little bit about your background.
Yeah, I'm Tom Langdon, and I came to Chevrolet Engineering in Warren, Michigan in 1963, fresh out of Johns Hopkins University. And I was assigned to a training program. Basically, I spent 3 years as a mechanic, changing cylinder heads and camshafts. And then I was promoted to engineer, and I happened to be at the right place at the right time, and they needed a guy to take over the high performance development program on the big block Chevrolet. My predecessor was Billy Howell, who had done a superb job in the fundamental development of the L88 engine. And I took over from him, I think in late 1967, to do power development and durability supervision of the program for the L88 engine, which developed into the ZL1 engine. So my job as an engineer was to write the day-to-day orders on what we were going to do to develop additional power on the L88 engine, and this eventually included the transition from the so-called closed chamber engine to the open chamber engine. And I guess I'll give a little more definition to what that really means as we get into the details.
Sure, and would you guys be able to tell us a little bit more about the Corvette chassis and the Corvette engine that we have in front of us today?
Well, this is actually an L88 engine, which is the cast iron version, or the lead version, so to speak, of the aluminum block ZL1 engine. And the benefit of the aluminum block, per se, for the Corvette was the fact that it weighed nearly the same or the same as the small block, so the weight balance on the car and the chassis was beneficial. And in my case, driving the ZL1, the performance value of the L88 and the ZL1 engine is immense. It's a rather fabulous car to drive, exciting car to drive, but the fact that it was better balanced than the initial cast iron block, big block, made it a much nicer car to drive. But this chassis represents essentially a standard Corvette of that era. The independent rear suspension, the mounting of the transmission to the cross member, the thing with the big block when it was introduced to the Corvette back in years before was being able to put this big block engine in the same chassis as the small block was designed for originally. So all that has taken place prior to getting to the ZL1, and the chassis demonstrates, you know, the packaging of the gas tank and the suspension.
So Tom, you mentioned before that the ZL1 engine was developed from the L88. Can you talk more about what the inspiration was for creating the ZL1 and what that process was like?
Actually, I can't add too much to that. Obviously, the ZL1 was an aluminum version of the L88, and that was inspired to save weight for better handling. Now, just a little background on the L88, which had been previously developed by Mr. Billy Howell prior to my involvement with the program, and that had been pretty highly developed for NASCAR application. And Billy had done a good job on that, and that engine at that time when I came into the program had been developed under racing conditions, been developed to approximately 550, 560 horsepower in racing conditions with open headers in concert with working with the camshaft that had been developed totally at Chevrolet Engineering. Now, in addition to that, it's good to know that there was a parallel program ongoing in North Carolina by Smokey Unick. So Smokey was developing the engine virtually identical to me at that time. So you could say that we were in competition with each other, friendly competition. And every 6 months or 9 months or so, Smokey would come up with some idea, and he would claim that he'd made some power increase, so he'd pack up his engines, bring his carburetor, ship it up to Chevrolet Engineering. I'd put it on the stand, and he'd stand in the dyno cell, and we'd run power runs on his engine to verify his supposed gains. And I had a lot of admiration for Smokey. He was a very innovative guy, and some of his innovations were true, and some of them were mostly they were not verifiable on my dynamometer, let's just say. So Smokey talked a good talk, and I had a lot of admiration for him. So when I got into this, as I was saying initially, the L88 engine was developed to around 560 horsepower with open headers.
And then we had also mentioned earlier that there was this transition from closed to open chambers.
Yeah, let me talk to that a little bit. The engine, as I received the engine to do development work, had what we called a closed chamber. And I think it's best illustrated on this picture of the combustion chamber itself. This combustion chamber, as we called it, had a closed chamber. That is, this side of the chamber was closed off. Shortly after I got into the program, a new cylinder head was designed to reduce hydrocarbon emissions. Ironically, this was for emissions. And a pair of the open chamber heads, which had this whole area opened up out to the bore diameter, right out to here, increasing the volume in the combustion chamber. And the idea was that the burn would continue and burn the unburned hydrocarbons which were being quenched in this area. Now, again, this was across-the-board modification on all big block engines, not just the L88. And that engine, that modification was done solely for emissions. But when I saw it, I looked at it and I said to myself, hey, you know, this intake valve is going to be more unshrouded. We're going to get better flow on this intake port. And so I immediately got the cylinder head down to the airflow bench and documented that there was a substantial airflow improvement due to the chamber, which ironically was from an emissions improvement, which was eventually implemented on all the big block and in a slightly different way on the small block also. In fact, also on the inline six-cylinder. Now, that change in the combustion chamber obviously reduced the compression ratio dramatically. I don't know, about 1.5 ratios. And so to retain the same compression ratio on the L88 engine, the piston required a modification on this side of the combustion chamber so that this dome was extended into this side of the combustion chamber to retain the same 12.5 to 1 compression ratio. Now, when TRW was the source for this forged piston unique to the L88, and when they did this modification to the dome, they also revised the pin boss area right here to include a mound of aluminum here. I can't give you really the background on why they did that, but this mound of aluminum had a slight area of porosity in it, which eventually, when we started running durability, this small piece of porosity here encouraged some cracks to develop later on in our durability test, thereby delaying the early introduction of the open chamber engine.
And that delay on the open chamber engine is what created the delay when we only built one, as far as I know, one Corvette with a ZL1 engine in it. And when I ordered the ZL1 Corvette as a company car, and that order sat in order heaven someplace for a long, long time. And the folks that were working for me kept checking with Tonawanda to find out where that engine was, because the engine was available and used in the Camaro. And so it was a little different dress and stuff like that. But apparently the change in the combustion chamber is what delayed the engine. So we had to wait a long time for it. And when we finally got it, everything was set in motion to build, what I think is, as far as I know, the one and only ZL1 aluminum big block Corvette engine.
Another comment that I think is good at this time is that the L88 engine that had been on Dynamometer for power development, I think that was in Dyno Cell 5, and I had two really, really good dynamometer operators that could repeat power tests one after another, after another, after another, within 2 horsepower. And when you're operating at 550 horsepower, percentage-wise, that's really, really a small number. But I need to point out that it's really important to have, number one, an engine that is stable from run to run to run. We had way over 100 power runs on it. And the engine that I had that was so valuable to the development of this this power improvement was very, very, very stable, in addition to having these really good dynamometer operators. And one of those operators is still in the Detroit area. His name is Russ Ouellette, and Russ ran my second shift. And he was the guy that called me up at 10 o'clock at night and said, "Mr. Langdon, we made the goal. I got 600 horsepower tonight." And that was quite a celebration, quite a celebration. But what I wanted to point out is this engine was so valuable, and it had the closed chamber pistons in it. So all the development of the open chamber cylinder head was done on a closed chamber engine. So the compression ratio was somewhat lower, about 11 3/4 was the compression ratio. So I knew when I put the open chamber heads on the closed chamber pistons, despite the fact of a reduction in compression ratio, we got a moderate increase in power.
So we have this very specialized engine that's producing 600 horsepower in different tests. So why was the actual horsepower of the ZL1 engine so much higher than what was publicly advertised?
Good question. Good question.
Probably for insurance purposes.
Well, I'm sure that had something to do with it. And the advertised power didn't have anything to do with the data that I generated. The advertised power of the engine was as it was sold to the customer, which had cast iron exhaust manifolds on it. The cast iron exhaust manifolds were not compatible with the camshaft that had been developed for racing application. The camshaft that was developed prior to my usage, the L88 camshaft, was developed with racing tubular headers. And that was a big development that Mr. Billy Howell had developed, the interdependence of the camshaft and the design and the specifications of the tubular headers. If you didn't have the two together, they didn't work well at all. So the factory combination of exhaust manifolds, particularly with a muffler system, was very, very incompatible combination of parts, to the extent that I ran some tests with the complete exhaust system, actually for a Camaro, in the application for Copo Camaros. I ran some tests where the horsepower compared to as it would have been installed in a Camaro with a complete exhaust system, compared to the typical application that it would have been run on the racetrack with tubular headers. The power was cut in half. We dropped the open exhaust header power level on this particular engine was about 530 horsepower. When we put the exhaust system on it from the Camaro, complete with cast iron manifolds, pipes, mufflers, the complete system, and ran it again, it produced 265 horsepower. That's how dramatic the camshaft, the racing camshaft, and the factory exhaust were incompatible. So we learned very early in the program, or Bill Howell learned early in the program, that the interdependence of the two systems were very, very important.
I think you also have to add in the accessory drive too, driving the alternator and the AIR pump if it's involved in the system. So there's a lot of draw on that too, but it does reduce the horsepower.
Yeah, I'd like to make a couple of comments about that. The numbers that we're talking about here today, about the rating being 430 horsepower, and I'm talking about numbers that are dramatically higher than that. These are all numbers that were actually generated on power tests But the power tests that we were running at General Motors at that time were quite different than what you see on TV today. There's some pretty good programs on TV today that show power development on a wide variety of engines. And these are tests that are run very quickly, maybe in 10 to 15 seconds, while the engine accelerates from 3,000 RPM up to maybe 7,000 or whatever the speed range is. And these are transient tests that are run very, very, very quickly over a very short period of time. The tests that we ran on all engines at General Motors, from the 6 cylinders up through the racing engines, we ran them exactly the same way. And for example, on an L88, the power tests were started at, I believe, 2,400 RPM. The throttle was open, the dynamometer loaded the engine till it was stable at 2,400. I'm going to drag this out a little bit just to illustrate. And as the engine was stabilized at 2,400 RPM, the carburetor was richened up through a system where we had very accurate control of pressure on the float bowl of the carburetor. And so we increased the pressure on the float bowl of the 2 float bowls on the carburetor to increase the fueling delivery to the engine. And we increased the fuel flow to the carburetor, to the engine, excuse me, until the power started to drop off. And then we would lean it out again, lean it out until the power dropped off, and then put a little bit more fuel in it. And that was called LBT, leanest for best torque. And then once we had the fueling right, we had a mechanical control on the spark advance. And so maybe we'd be running at 25 degrees of spark advance, and then we would increase to 28, 30, 32, and watch the power increase. And then when it got to 32, we went to go to 34. 34 was too much, so we'd back it off to 32. And then we'd go back and say, well, let's check the fuel again. We'd lean it out again, lean it out, and then go back and check the spark again. Now we're ready to take a data set. And they were, back in the day, these were all taken by hand. So you'd write down the oil pressure and the water temperature and the spark advance and the fueling rate and the manifold vacuum. And that's about 3 minutes of talking here. That's how long it took to take 2,400 RPM. Now we'd go up to 2,800, spend about 3 minutes there. The next one was every 400 RPM. I'll tell you, when you get to 6,800 and you're leaning out the fuel and getting it right, we go a little too lean till the point where it would lose power, and then you put a little more fuel back in it. Then you'd start with the spark, start out about 35 degrees, give it a couple more, get it up to about 40. Maybe it wants 42. Let's try 42 degrees. No, 42 doesn't give me anything. We'll back it off to 40. That was called MBT, minimum spark for best torque. So we're running at leanest fueling rate for best torque and minimum spark for best torque. You can't do any better than that. So every camshaft that we ran, every carburetor that we ran, every exhaust system that we ran were run under these ideal conditions. Steady state, about each speed every 400 RPM. So you got a complete shape of the curve starting throughout the operating speed range of the engine. And that data was corrected to a standard SAE set of conditions, a barometer of 2992, 29.92, and a 60-degree carburetor air temperature and a certain relative humidity. Every data set was corrected to that set of conditions. So these were very, very reliable, very, very stable conditions. Quite different than these quick Now the numbers are fairly comparable. I'm not saying that our numbers were more meaningful. I'm just saying that we got a pretty good semblance of the durability of the engine and its sensitivity to severe operating conditions. Now, what allowed us to do all that, and in my 3 years of running tests like this, we never had an engine failure on the development. We had many durability failures, but on the development, there were a few things that we did that I feel were very important. I call them insurance. When we ran these engines under these very conditions, when we're running engines oversparked and underfueled, we're running them too lean and oversparked, we ran aviation gasoline. So it was a 135, 120 octane numbers, aviation fuel. We were running aviation oil, ashless aviation oil, which has no cleaner in it, no detergent package in it. And we were also running, I'm trying to think what the other insurance, oil and gasoline. So, and this was like buying insurance, never had any combustion. Oh, and very, very cold spark plugs. That was a key. We were running 41 heat range AC spark plugs. So with those precautions, we didn't have any failures, even though we oversparked the engine and ran it leaner than it wanted to run, just to find out what the optimum power was on these engines.
So why did so few of these ZL1 engines get designated for Corvettes?
George, can you answer that?
My understanding, and this is, might say kind of secondary, that the ZL1 engine, of course, was released for the Camaro for racing purposes and that kind of stuff, and it was being sold, commercially, and the Camaros were extremely fast, and because of the benefit of the weight advantage for the engine, were high performance. But if they're used in the hands of the average public, they were a fairly complicated car to operate and do, I would say, safely. But the reason I think that they didn't get into the Corvette was that I think there was an issue, I assume, within the corporation that the engine provided the same amount of danger in a Corvette, and so I don't think they were too excited about having a lot of Corvettes out there with this engine package in it because of its performance capability, and didn't process the orders. I think it was, I'm guessing, was held up at the order level and at the sales level, because I know when we put our order in, it was, as far as I know, was a one-of-a-kind thing. And of course, we were issuing it as an engineering entity at the assembly plant. That's where my organization was. We were resident engineer at St. Louis, and we had responsibility for the full-size car and the truck and the Blazer and the Corvette. And I had a staff, and we found out through the engineering process that this engine had been released in the Corvette. And of course, I'd have to say that the folks that were in my group were pretty excited about the thought of a lightweight engine in the Corvette, and very familiar with the LA88 performance. So they talked me into ordering it as a company car. We had a number of cars that were being used in my group with manufacturing plates on it, that just everyday cars, but as far as the full-size car and truck goes. But so I ordered it as a personal company car, because that way I could get the order through, and it went through. But as I said, it was, quote unquote, forever getting the car, because I needed to replace the car I was driving with a company car, and that's what got into the discussion on the delay of it. But and part of the delay, we believe, was the engine thing. But I think that the salespeople, through input, I'm guessing from the insurance companies and anybody else, about not wanting these engines out in the general public. I think there was even some dealers that were concerned about the ZL1 and maybe even the L88 for that matter in the Camaro, that the performance was so extreme for the era, no matter what the horsepower rating was and the configuration of it. This was a super high performance car when I had it and when I drove it, and it was really something to drive. I think that I've mentioned to some people here that at one time I owned a gas dragster with a supercharger on it, and I turned some pretty good times back in the old days in the 60s with that car. And this thing was as exciting to drive as that was from my perspective, and the handling on it was great. But I think the salespeople decided from the input from the dealers and the corporation that maybe we ought not to have too many of these. And I think Zora wanted it released so that we could be homologized for racing and that kind of thing, which made really good sense. And it's just turned out to be, as it turns out, as far as I know, a one-of-a-kind, single-built production vehicle, and built by General Motors and by anybody else. So I think it's one of the rarest cars, production cars in the world.
Would either of you gentlemen be able to talk about maybe the testing process for the ZL1? I'd heard that there may have been some other Corvettes outfitted with ZL1 engines that were considered engineering cars that didn't make their way out to the public. Were either of you involved with that?
I know it was 88077 was the company car number, and I pulled that right out of my head. I did not plan or look that up, but that car was infamous. And it was a street-driven car with an L88. It was an engineering car. I had occasion, I didn't even have driving privileges back then, but I did have occasion to drive that car on the track at the tech center. It was equipped with headers. It did have mufflers on it, but it did have headers on it. It was quite the car to drive, and it survived many, many different drivers. I don't know beyond that. There probably was a development car at the proving grounds, but I know nothing about that. I guess you got to remember to put my commentary in perspective. I was, at the time, I was a sixth level development engineer in the Dynamometer lab, working for a totally different organization than Duntoff's organization. Zora, I knew Zora, and he would come down occasionally to observe what we were doing on Dynamometer, but I did not work for his organization. It was a separate organization. And so I'm sure that he would have had at least one car at the proving grounds doing development work.
Yeah, I'm sure that there was a number of development vehicles. Because I was stationed in St. Louis, I had been removed from the engineering center for a number of years. I'd had some assignments in Baltimore, and the St. Louis assignment was another assignment. And so I was not aware of the development, as it turns out, of the ZL1 engine at all until the folks in my organization began to dig into the Camaro thing out of interest, and then found out that it had been in the release system. And when we ordered the car, we knew it had been released for the Corvette, and I don't know what machinations had to be gone through to get the order through the system as far as the Chevrolet organization itself, as far as building the car, which is, you take the Chevrolet specifications from the engineering center, and they get integrated through the system into an order base, and I think that probably took some time, but that was probably, I'm guessing, driven by Zora, because I was not privy to that. But the thing is, the other thing that happened with the ZL1 engine, of course, it became available, in the aftermarket. As it turns out, over the years that I worked with a number of people in the development group out of the Arizona Proving Grounds, a couple of young guys that were actually from Oklahoma who did a lot of racing out there, and they had purchased a number of ZL1 engines that they used in the kind of racing cars that they had out there. So the engine became available as an engine. It was mainly produced in Camaro, but we have this one that ended up in the Corvette, which makes it a very special car. Through a lot of work from a lot of people like Tom, that took the basic design of the L88 and we were able to develop the aluminum block to withstand it. Aluminum blocks are, I think, fairly common now today, and we use a lot of them in Corvette, obviously, that kind of stuff. But at the time, that was a real breakthrough. The aluminum heads on the Corvette were a breakthrough back in the day. And so you take the aluminum heads on the L88 and you put an aluminum block under it, and you got a pretty special product.
You brought up Zora, and I have to interject here. When he would come down to Dynamometer, he referred to this engine, the big block, as Big Moose. And when he would leave, he would just shake his head and he would say, "Big Moose hunks." and I always remembered that.
A lot of torque.
Yep.
A lot of torque.
Well, George, you mentioned it a little bit before, what it felt like to drive the ZL1. From what you remember and what you experienced, did Big Moose honk?
Yes, it did. As a matter of fact, the ironic thing about the car, when they finally got the car built, and when I ordered it, you can't get very much in the way of options on that particular engine or even the L88. So I ordered it with a side-mounted exhaust and positive traction and all those kinds of things, as much as you could get with a car. And we got the car, and they finally got around, finished painting the mustache stripe on the front, which was, I say, from the plant standpoint, was the big deal. That was the discriminator for the plant on the ZL1 Corvette, was the mustache stripe. So they got that on, and I finally got it out of actually. That was done, I believe, my memory says it was done out in repair rather than online, because there was no online station to do it. I'm not sure that's absolutely true, but I believe that's the way it went. When they finally got that done, then I got the car and I took it and I drove out of the plant and was on the way home, and I'm driving on the freeway out to where I was living, and a driver came alongside of me and motioning to me and pointing down, and I rolled the window down, and he says, "You're on fire." And the side-mounted exhaust had been put on, and they were too close to the exhaust pipes, and the fiberglass liner was beginning to smoke. So I could see the smoke kind of coming out, so I looked for the next exit, and I turned it off. It was to the airport. So I drove it into the airport service station, because back in those days, they had a water dispenser. So I got out, got the water dispenser, and I sprayed underneath the thing to kind of cool it down and get rid of the smoke. And of course, I'm at a service station with a smoking car, and the people who were standing there were a little excited. But that car really had performance, and that was the first time, driving out of the plant. I got as far as the airport, and I said, this is really going to be something. I drove it the rest of the way home and never had another problem with it, and we finally adjusted it. But the performance of this car was, like I said, it was as close to anything racing as you can get, because I think the balance on it, made it, it was a noticeable difference. And I'm sure that's why Zora was so excited about being able to homologize that particular feature in the Corvette. Years ago, when I first started at the engineering center in '63, after coming from the plants, I worked on one of his other projects, was the 36-gallon gas tank. And that was a problem because it was a fiberglass tank. They found out that fiberglass does not hold gasoline, and it was permeable, so we had to go back and forth to Molded Fiberglass Body Company, and I flew back and forth to try to get that system running. So the ZL1 engine and the 36-gallon gas tanks are the two things that I associate with a Corvette and performance that you had to really work on to make work.
And then, George, could you clarify the timeline for how long it took to, order and build this car, just from your perspective, and then how long you were able to essentially own it and drive it?
Well, that's going back quite a ways, and I don't remember the timing, but normally when you would order a car, in those days you could order cars and get them built to your specifications, so to speak, and that normal order time would be 3 to 6 weeks type thing, and this was, my recollection was quite a bit longer, and I don't know what the number was, but it seemed to take forever. And as I said, the reason that was important is because this was destined to replace the car that I was driving as a company car, and somebody in the plant who wanted to buy my particular company car, which is a feature that we used to offer the employee for company-owned vehicles, was anxious to get the car, and I was going to be putting a lot of miles on it. So it was a significant thing, but I don't remember the time. But it was quite a bit longer than normal time because of the and when we checked the availability of the engine, I think it was the design changes that necessitated to do it. Plus the fact all the engines initially have been designated for Camaro, so making sure the accessory drive and stuff like that was correct on the engine out of Tonawanda was, and that's who we worked with eventually to get the engine to the plant so that they could set the build date for it.
And then can you talk more about, I believe you were transferred away from the St. Louis plant, or maybe what caused your separation with the car eventually?
Well, the car, when it was built, ironically, it cost $10,771 or pretty close to that, which was probably more expensive than any production-built car in General Motors. I think I was more expensive than any Cadillac that you could get. Maybe some of the special Cadillacs were a little bit more than that, but at $10,771, that was the most expensive car. And so the plant was the one that was responsible for getting rid of it, and the gentleman that was going to replace me as resident engineer didn't want to drive the car. And so I don't know whether we got the full 3,000 miles on it, which was needed, but they decided to sell it. So I had to go up and sit down with a fellow by the name of Owen Ellis, who was the comptroller at the plant, because his department was responsible for selling the car, and they were concerned about where were they going to sell this car that would actually cost twice or 3 times the amount of the normal Corvette with fewer features on it, no air conditioning and that kind of stuff. So I suggested that at that time I think we had 21 Chevrolet zones in the United States or something like that. And I said, well, you need to canvass the top 5 selling zones and see if they want the car. And so that's what he finally did, and they were able to find a zone that would take the car and try to sell it through a dealership there, because nobody in the plant could afford to buy it, even as a company car, or whether they wanted it or not. That was $10,000 for a Corvette in 1969 was a lot of money, and the market wasn't very big, so. It was sold to the dealer organization, and it went on its merry way. I think there's a lot of stories on who bought it and what they did with it, and that's a feature in itself.
So the Corvette ZL1 that is in Roger Judski's collection that George used to own, how do we know 50 years later that this is an authentic ZL1 Corvette, or potentially the only ZL1 Corvette?
Well, the only thing I can add to that is that I know that we had enough trouble building the one that I drove, and I know how long I drove it, and I know when it was sold. If the serial number of a ZL1 is after that particular serial number, then I can't really speak to that. It's possible. As far as I know, that in talking to, because I left the St. Louis organization, I went back to the engineering center on a different product line, ironically, and that I don't believe that any of those folks ever told me that there was another ZL1 built. And if the serial number is after that, then I guess you can make a case for it. But any car that is portrayed as a ZL1 production built car with a serial number before the ZL1, I could say is not a production built car, because we had enough trouble building the first one and getting the pieces together and getting it through the system and all that stuff that goes along with a production car, that we're fully aware of the order of magnitude of accomplishing that goal, that anything that's got a serial number before the ZL1 Corvette, I would have to say is not an authentic car. If the serial number is after it, there's a possibility, but not a probability, because the folks that, you know, I had 2 engineers on Corvette, and I know that they are never been aware of another one built. So as far as I'm concerned, there is only one production one from my basis.
Do you want any more comments about the development of the extra 50 horsepower that we did over the next couple of years on the L88 and then up through the ZL1?
Yeah, let's talk about what that process was like. And it's was the goal there to maybe get extra horsepower out of the engine, or to see how high you could go, or we can talk about that.
Continuously, every single day.
Never ends.
That was my goal. I mean, I was a lucky guy to get this job. I would wake up every day with a smile on my face. I couldn't wait to go to work to find out what had developed the night before. And I would be remiss if I didn't include, I don't want to get off on too big of a tangent, but at the same time, with the same engine, I was also running a parallel program for the Chaparral. The Chaparral being the Group 7 racing activity at that time, with no limits on the intake system. So I was also doing development work with fuel injection, the Crowler style fuel injection, and that dictated experimentation with other camshafts and other exhaust systems peculiar to the Chaparral car, and its usage of a 2-speed automatic transmission. So that was a somewhat different program, but basically I was given free rein to do whatever I thought was going to be good. So I had an unlimited budget on 2 racing programs with 2 shifts, two shifts per day to run. And that was a wonderful time in my life. When I was introduced to, shortly after I started on the power development program, taking over from Bill Howell, a pair of cast iron open chamber heads appeared in the dynamometer cell, and I was told, this is what you're going to deal with, see, in the future. This is what's coming down the road in 1970, and see what you can do with them. So I put them, as I previously mentioned, I put them on the airflow bench. They looked improvement. Shortly, there were some improvements in airflow on the intake side. Shortly after that, the aluminum head version came to me, and I immediately recognized that we needed to harness all the hot rodders in the world. So I got 5 sets of aluminum heads. I sent them out to all the racing shops that were prominent particularly in the drag racing, which I was familiar with. We sent them to Mondello, we sent them to Smokey Unick, we sent to Bob Schaefer in Detroit, Butch Elkins in Detroit, Airflow Research. We sent them all out and said, give us your best shot. When we got them back, we airflowed every one of them, and then we took and we dyno checked them also. We took the best exhaust port and implemented the changes, including a bigger exhaust valve We went from a 1.84 to a 1.88 diameter exhaust valve. We unshrouded the exhaust valve, same on the intake, increased unshrouding on that. We implemented them revised the design of the ports in the combustion chamber to improve the power level. And at the same time, I set out camshafts to all the different camshaft manufacturers at the time, and I knew who held the NHRA drag racing records, and if they had a big block, that cam guy got a camshaft, and they sent back their recommended camshafts for a 4-barrel application. And so we ran off Iskandarian and Engel and Urson, and I can't remember them all, but we had a camshaft manufacturer right here in Detroit called General Kinetics. And General Kinetics had some very, very good cams. And not only that did they have good cams for power, but their cams were very good for dynamics. So once you get a camshaft that's good for power, the next thing is you got to run some durability on it. And we had a durability fixture where we would motor the engine at very high speeds. And with an optical displacement follower, you would follow the dynamics of the opening and particularly the closing of the valves, which is the primary thing that affects the durability of the valve spring. And if you look at what failures on the big block, invariably they were valve train related. And so we had to go through, it's not just finding power, it's finding good dynamics and getting those implemented. And so we went back and forth with General Kinetics numerous times. And then once we got a General Kinetics cam that worked good, then we took the dynamics of that camshaft, we put it back through the Chevrolet design features, and we came up with the ZL1 camshaft, which is different than the L88. Not a lot different, but it was like 10 more horsepower and had a good durability. So we went through this iterative process on the cylinder heads and on the camshafts, and then once we settled down on a combination of camshaft, then I had to go back through the exhaust system. Now, I had been given this very well-developed 2-inch pipe diameter exhaust system. I logically said, well, you know, we're at a higher power level, let's try some 2 1/8 inch power. So we went through, and the 2-inch pipes that I had been given optimized out at about a 36-inch length. When we ran the 2 1/8 inch, they optimized out at 38 inches of pipe length. And then so we made more headers at 2 1/4 inch diameter, and they optimized out at 40 inches. Very slight power gains, but the important thing is when you fabricate a set of systems for a car, like they did for the Corvette, the side exhaust, all the pipes are not really easy to be the same length. So you can get the same tuning. If the pipe had to be, I'll say, too long, you could make it at a slightly bigger diameter and get the tuning virtually identical without having to sacrifice power because the pipe was too long. So we would run 2 1/8 pipes at 36 inches. We'd run them at 38 inches, 40 inches, 42, 44. And that was a set of power runs, all run with this GM Test 20, where we optimized the fuel, we optimized the spark. Everything was given a fair chance and optimized fueling and sparking. And we also went through different intake manifold upgrades. We evaluated different carburetor sizing, although the carburetor sizing was dictated by NASCAR. So our guidelines were dictated primarily by the NASCAR rules and then implemented into the L88 and ZL1 designs. So once we got all this worked out, then a series of, I think it was 5 engines were built, and we were going to run durability. And the durability tests were different. We had 2 different durability tests. We had a stock car racing durability where the engine cycled at wide open throttle from, I think, 5,200 up to 6,800. And then it would close throttle, come down to 52 again, and go up to 68. And that was, and every 5 hours we would shut the engine down, and we would check valve lash and check compression on it, and then put it back on test. The goal was to get to 25 hours. We blew up a lot of engines getting to 25 hours. So, and they were, piston pin locks were coming out. We talked a little bit before about the open chamber pistons, had a piston cracking in the pin boss area. On the aluminum block, aluminum head engines, we noted that there was a head gasket problem, which required an additional head bolt being put into the ZL1 block, and a lot of valve spring problems caused by the dynamics. You got to remember on this engine was very heavy valve train, and at that time we were very restricted as to what kind of technology would implement. If you compare the technology back in the day that was allowed by our management, by General Motors, it wasn't that there wasn't technology, but if you look at the technology implemented on today's LS engines, for example, that have titanium intake valves, hollow stem exhaust, that was not even, you could not even talk about those kinds of things. Titanium valves, titanium connecting rods, can't even talk about that. You'd be laughed out of the room if you brought that up. You'd lose all your credibility if you brought that up back then, back in the day. So the valve train was very heavy, and that was a major problem back in the day.
One of the things that you mentioned that maybe in this conversation that's unique is this is a carbureted engine, developing that much horsepower, that much torque, really, that kind of stuff. And a carburetor, as he pointed out, the adjustments on it can be made to benefit it. Very difficult to do, but you're talking about production engines, and every carburetor is theoretically supposed to be the same, goes on the car, and gets the performance and the horsepower that it's supposed to get. But to develop an engine like the ZL1, with its lightweight and the characteristics that were developed over time, the aluminum block, the aluminum heads, and camshafts, and the things that he's described, along with a carburetor that Holley makes and were assembled on the car, and to get that kind of performance in a variety of products and that performance being so outstanding is really amazing, I think. Again, it's a production vehicle. And that's the thing that is really important in this discussion. This is not a hand-built car. This is built in a production on the line with everything else. And it was truly an amazing vehicle.
Yeah, thanks for bringing up about the carburetor, because this carburetor was unique in a couple ways. The fuel bowls were developed in conjunction with Holley Carburetor Company, and they were used, I think, for 1 year proprietary to General Motors. These were so-called end-hung float bowls, which dramatically improved the cornering capability, which was very important to the Corvette. And another thing about the carburetor, although Billy Howell had done a pretty good job in developing the fuel distribution of this carburetor, he had developed what they called stagger jetting, so that all 4 jets were different from each other to try to get as close as possible to an I won't say perfect, but an acceptable level of fuel distribution. and the carburetor had 4 different jets in it depending on where you were trying to get the fuel to go. But we still had one cylinder that was running close to 14-to-1 air fuel ratio when you're running at LBT fuel. So you were running one cylinder that was way leaner than optimum, because there were other cylinders that were running richer than optimum. Carburetor is not a very perfect thing, but it's pretty simple. It's pretty simple and it's pretty cheap. And that's what we were stuck with. We did the best we could with it.
So, Tom, all this performance testing that you've been talking about, the durability testing with the engine and the data you collect, does that information help you innovate or design new engines in the future? Or is it so specific to the engine that you're testing that it doesn't really have an impact on the future work that you do?
Well, certainly the knowledge that we gained, the interdependence of the camshaft and the exhaust system was instrumental. That information I found out from talking to Bill Howell. That information was not known on the predecessor to this engine, the 409, the W engine. That engine was not developed with open headers, and so that stunted its growth. It could have been much higher in power level, not as good as this engine, but as Smokey got into this and as Bill Howell got into the development of this engine, the tubular headers just opened up another 50 or 100 horsepower by being able to use the go a lot longer in duration on the camshaft if you had the exhaust to go with it.
Well, I'll say again, number one, I didn't own it. General Motors owned it, and I got to drive it. So that's one of the true benefits of working for General Motors. And General Motors makes a lot of cars, and over the 41 years I worked for them, I drove an awful lot of General Motors cars, all the way from the ZL1 Corvette, and I also was responsible for the Chevette, which is a 4-cylinder, and we put a diesel in it. So I've driven everything. But the performance, again, I'll go back and say that back when I was a little younger, and I owned an A-gas dragster, which was a small block Chevy board and stroke with a 671 blower on it, with an Enderle fuel injection, by the way. Pete Enderle, we were running out of Bakersfield at that time. Pete Enderle put these huge 40 square inches of Venturi of fuel injection capability on top of the 671 blower for a 341 cubic inch cast iron Chevrolet engine. We ran the dragster, and back in the 60s we were in the 160 and 8.5 second time, which was good enough to come in second at the Winter Nationals when we had the car. But the performance of a dragster is you're going from 0 to 160 miles an hour in 7 or 8 or 9 seconds, or whatever it happens to be. This car, of course, wasn't that fast, but the sensation of driving it, because it was a 12-second or 11-second or 13-second car and a quarter mile perhaps. It was never on, but it felt just the same as a dragster. Like I say, and I think the people who know me said this was the closest thing that I ever drove that was the closest thing to that dragster.
So was the ZL1 your favorite among all the GM cars that you drove, or where does it rank?
Well, yes and no. I mean, I happen to love performance and that kind of stuff. I've driven quite a number of other General Motors cars, obviously. I even drove the turbocharged Chevette, which was a 4-cylinder, and that was an interesting car because it was so light to drive, so interesting to drive. I've driven all of the Chevrolet products as company cars, and I like them. But the thing that sticks in my mind after all these years, and it's a lot of years, is the performance of this car. I can still remember it to this day.